Hey, welcome to the surface area installment on measurement, and let's look around the screen. And surface area, that's the area of the outer surface of an object. Sometimes it's going to be a three-dimensional object. We've got some little examples around the screen here. And why would we want to measure the outside area? Well, we might think about that for a minute, and this is a funny shape in here. We put a grid over it. Wonder what's going on there. There's no formula for that particular shape. It's called irregular. Well, some of these others are known cylinders and spheres and stuff. And what's this over here? Uh-oh. That's the reason we're going to look at surface area. One of the biggest applications, of course, is if you want to paint an object or cover it with carpet or a covering of some sort. So the paint, I just put the paint there. Just remind you, those tins of paint will cover so many square meters. So if you're going to paint one of these three-dimensional objects, you're going to have to work out the outside surface area. Okay, so that's where this fits in. So it's taking it to another dimension. What dimension? 3 dimensions. Well, yeah, there you go. All right, so let's have a look at how we do these now. So surface area of a three-dimensional figure with plain flat faces is the sum of the areas of the faces. So let's do this easy one here now. This is a triangular prism, if you like. Then you could lay it out. This is called the net, the flat two-dimensional picture, which when folded up will create that three-dimensional shape. So you don't actually have to draw that every time. What we're basically doing is looking at all the faces, two ends, the two sides, back and front, and the bottom. That's what we're trying to do. All the outside surfaces, break them down into common shapes. Okay, let's have a look and have a look at a rectangular box. You can draw this if you wish, or you can just list them out like this. So what do we got? At the sides, we've got a side here and a side over there. It's two faces, 2 by 3. Front and back, two faces, 2 by 4. And top and bottom, there and underneath, two faces, 3 by 4. Okay, so the total surface area is you add them all up, add all these up and get square centimetres. Don't forget to put the units on there. Okay, so that's going to be handy if we want to paint it or cover it in some way. Okay, that outside surface. Are you ready? I think it's important now to have a go at just a few there. Hopefully you've done a bit of this before. 3 questions, pause presentation, have a go. We're also going to look at the cost there to make it a bit more practical problem. Why would you want to work out a surface area, work out how to paint it, and therefore you want to work out the cost of the paint and so on. Okay, I'll show you the answers now. Some answers for you there. Okay, have a look at those. Let's move on and build this up a bit to some more interesting stuff. So here are some of the common figures that we might want to look at in three-dimensional shapes. Cylinder, so the curved surface around the outside is 2 pi RH. You might just get an idea of where that formula comes from if I snip this up here, cut it up there with a pair of scissors or something, and lay that curved surface out. It would lay out like a rectangle, wouldn't it? If I cut it right through the side there and laid it out, it'd be flat. So this distance around here would be this distance here, laid flat. So that's the circumference of the circle, which is 2 pi r. And then the height there would be the height. So that's explaining why the area of the curved part of the cylinder is length by breadth 2 pi RH, because the curved part of the cylinder can be laid out as a rectangle. And then if you're closing in just one end, you've got the curved surface and one end. If you close in two ends, you've got the curved surface and two ends, because the area of a circle from before circular their end is pi r squared. So just breaking everything down into all those exposed outside surfaces. Sphere, you can't do this one by reasoning. This one you have to do again by calculus. The area of a sphere, the outside surface, is 4 pi r squared. So you just have to use the formula. We're going to do the same thing with a cone. Later on we might have a look at why it is like this, but in this course, the curved surface there has an area of pi r s. S is what's called the slant height, the height down there, pi r s. And then if you close, it's got a bottom base here underneath, so it's got a circle added on there. So to paint a cone, you need to paint the curved surface, pi r s, there, and plus the end. Okay, are you ready? Let's look at some of these. These are common shapes, often used in practical applications. Let's have a look. Find the outer surface area to 1 decimal place of a cylinder. It's hollow top and bottom, so it's only the outside surface, which is 2 pi rh, and putting the numbers in pi r and h. Look at the diagram, use all the numbers from there, and don't forget the units, and we've rounded it off, so it's approximately. And a sphere, radius is 8 centimetres. Write the formula, put the numbers in, state the units. And then the cone is just the curved surface by rs, because it's hollow. There's no bottom to it. It's like an ice cream cone or something. Okay, so pi by r. Remember, s is the slanty height. There. Okay. Then state the units. All right. Okay, well, let's have a look now and give you a few to do here. There's 17, just checking your formula now and practicing. Pause it, have a go. The answers are down below. Have a look at 18 now. So if we can get them all on. No, we can't get them all on. 18, 19 and 20. Interesting shapes. Glass houses or growing tents to put seedlings and things in. Okay, good practical application. And 21. Okay, have a go and start to think about how useful and important this is. Okay, and I'll show you the answers. Okay, so here are our answers for those problems. Alright, well, I've got a little inkling down here, you've got a little inkling about what this next thing's about, and that's of course conversion of units. Because often you will be working in centimetres perhaps, and on the can of paint or whatever it's per square metre, so you must be able to change square centimetres to square metres. So here are our units. A square centimetre is 100 square millimetres. Square metre is 10,000 square centimetres. Hectare is 10,000 square metres. Now, the easiest way of actually looking at this one, let's look at this one here. A centimetre squared, let's do it, a centimetre by a centimetre, is 10 millimetres by 10 millimetres. So that's actually 100, 10 by 10, 100 square millimetres, not 10. So although there are 10 centimetres, 10 millimetres in a centimetre, because it's area, it's length times breadth, and it becomes 100. So just watch that. And a metre, let's draw another diagram. A metre by a metre is 100 centimetres by 100 centimetres. So 1 square metre is not 100 square centimetres, it's 100 by 100, length by breadth. So it's 10,000 square centimetres. So just watch that. So these little diagrams up the top here help you see that you can't use the centi and the milli quite the same way with area, because you're multiplying two of them together. So here's a conversion diagram, of course. If you've got big ones and you want how many smalls, then you'll times, get a bigger answer. Coming back the other way, you'll divide. So it's a big to small approach again. So have a look at that diagram. You might copy that down, see if that helps you. Let's do some problems here. Convert 650,000 square metres into hectares. Now these, relative to hectares, these are smalls going to bigs. We're going to divide. Okay, so you're going to divide by how many square metres in a hectare. You've got to know that one off. 10,000 square metres in 1 hectare. So you divide it. 2.5 square metres into millimetres squares. These are large or bigs, if you like, going to smalls. So you're going to have a larger number of smalls. So you're going to multiply. And don't forget, square metres into millimetres, there's 2 stages. Right? There are 10,000 square centimetres in each square metre, and then you've got to go to square millimetres. And there are 10 by 10 or 100 square millimetres in every square centimetre. So it's a biggie. Lots of multiplication. So this is going to change it to square centimetres, change it then to square millimetres, and then state your answer with the units. Okay, same as what we were doing before, only you've got to keep your wits about you with the squares because it's a different number. Okay, and let's just remember there's 100 square centimetres in a square metre, but in 100 centimetres, in a metre, but there's 100 length times breadth, a lot bigger number. You can't use centi anymore. You've got to sort of use centi squared, if you like, 100 by 100. Okay, have a go at these conversions, and it's very important in practice because people measure in all sorts of different units, and you, being a budding young mathematician, will be responsible to interpret that to a unit that is most appropriate. So something on the can, per square metres, you need per square metre, not per square centimetre. All right, let's have a look at the answers. Okay, some answers there. Okay, let's go on and finish this little unit off now. And here we have that picture that I gave you before. Areas of irregular shapes. That is, they aren't known geometric shapes, cones and things like that. These happen to be flat shapes. The area of the leaf here, okay, and the way we can do it is an approximation. There isn't an exact mathematical formula for this, by placing a grid over the shape. So you can see we've done that here. And then we have some rules. If it covers a full square, you count as 1. More than half a square, you count as 1. Less than half a square, you count as 0. So it is only an approximate method. Okay, find the approximate area of the leaves shown by doing that counting method. Okay, if it's less than half a square, you ignore it. More than half a square, and you hope they'll balance out and get a rough number of squares covered. I think this really brings home the idea of area, doesn't it? So you can see here, area is a number of squares contained within the figure there. Okay, and we'll assume these are centimetre by centimetres. Alright, so let's have a look at these couple of problems. 25, let's just bring it up here. 25 through 28. And you can do these last couple if you want, just thinking about this as a method. Alright, let's have a look at the answer then. Oh, haven't got the answers for that one. You'll have to look that up in the book. Oh yes, I know why. Because here, yeah, it's only the top one. This of course, these don't have specific answers. Your shoe and your foot, everybody's going to be different. So you might look at this discussion thing and check the answer for that in the book. Okay, let's go down and do the last little bit, which is a technology thing. here's some problem solving with technology. Okay, so this is the design problem, rectangular duck enclosure of area 100 square metres. And what you've got to do is make up a formula now. So this is a little bit different. I want you to try and follow the instructions here. And what we're going to do is to graph it with a graphics display calculator using technology. So you take this formula, you put it in graph mode on the calculator, and then you want the minimum length. So you read the problem later on. So any minimum in graph mode, you can go, this is on the Casio, you can go Shift F5, which gives you GSolve, solving a graph, and then you can choose max or min. You want min, and then you can read it off. So try those two problems. Need a little bit of help from your teacher here for those, I think. Okay, but you're going to use technology. Alright, so let's have a look at the answers to those. So here are the answers. How to construct something which will have the minimum length of wire or something like that. Quite a handy little problem. It's attached here to surface area. It isn't. It's associated with surface area, but a bit more detailed problem there. A bit harder problem. All right. How are you going? What do you reckon we've got left? We've still got volume to do. So I'll catch you later on as we look at volume.